This is how the final product looks like. For the camera I'm using the printed flexible mount, which is holding on the Velcro, and the camera is fixed by the Velcro strap. The antennas from the receiver I mounted into the heat-shrink tubes supported by the zip tie. This is classic approach, I think. The motors are soft mounted, and shame on you, Eukfly, you provided only one set of short screws and only one lock nut, so I had to use my own screws because the provided ones were too short for the 4mm arm and the dampening silicone pad. So I think we can try the first run. Some short line of sight flight, only few punch outs, hover, few rolls and flips, record the data to the black box, and then analyze them on the PC. In BetaFlight configurator we need to set up few things for the filter analysis. We need to set the black box logging to some reasonable rate. And we also need to enable debug mode nudge for logging the raw gyroscope data. So let's set the debug mode to nudge. And let's do some flying. So arm, and now start very slowly with the throttle. Do some punch out. And let's analyze the black box. Now we will open the log file in Black Box Explorer. Select the log file from the quadcopter, and there are two flights. I actually did another one, so I select the second flight. We will be interested in this flight area, and we need to set up the graphs first. For the filter analysis we will need the gyros. I am using no smooth and 100% expo, so the graphs will not be distorted in any way. And we also need the selected debug nudge graphs. Let's name the graph as gyro pre-nudge. Save the changes. So now we can see in the bottom graph the unfiltered gyro data, and in the top graph the filtered gyro data. The most important tool for the filter setting is Spectrum Analysis window, and you can find it on the right side of these lines descriptions. So first we look to the pre-notch raw gyro data on the roll axis. It takes a while for computation, and we have a histogram of frequency spectrum in the selected flight area. We can unzoom it a little bit. So what we can find in this graph, there are highlighted areas which describes our active filters in BetaFlight. Because I am using the default values, I have all gyro notches enabled, also the D-term notch enabled. So as we can see in this graph, we have a very little noise in the motor spectrum, which is from 150 Hz to 500 Hz. In this area, the dynamic filter operates. So if you do not have any noise in between 100 Hz and like 500 Hz, you can safely disable the dynamic notch because it doesn't bring any filtration at all if you have this area clear. Also, if you have a noise on the higher frequency than the 500 Hz, the dynamic filter will not affect it. So then you have to use static notch or some other filter. So we have some noise peak in this area, and it's about 538 Hz. So the dynamic filter will not affect this peak of noise in any way. The second biggest peak is then about 1800 Hz, but this peak will get attenuated by gyro low pass filters quite well because it's on higher frequency, and we have a gyro low pass cutoff at 90 Hz. So the difference between 90 Hz and 1800 is pretty big, so this peak will get attenuated quite well, quite high. We can check this on filtered gyro, and you can see that the huge peak became a very little peak. So we check also the pitch axis. We can see that this noise spectrum is kinda different than on roll. The most prevalent motor noise is around 900 Hz. Also, this is not affected by dynamic filtering at all. This area for dynamic filtering is pretty clear already. Yellow spectrum is similar to the pitch spectrum, but with less noisy signal. Like the maximum amplitude of the noise is lower than on the pitch axis. The first thing we mentioned is that we have a pretty clear motor noise area, this lower part of spectrum. So we can disable all static notches on the gyro, and also we can disable safely the dynamic filter notch. Also, we can probably switch from biquad filter to PT1 filter. because, as mentioned, the motor noise spectrum is very low, and the high frequencies get attenuated quite well also with PT1 filter. Yeah, you can see the filtered gyro pitch is already quite nice. My only concern is this little peak, about 86 Hz. I think it's some kind of the noise. It shouldn't be there. So we can lower the gyro low pass filter cutoff from 90 to 80 Hz. And this small peak gets a little bit more attenuated by gyro low pass filter. This is our first guess. We set the values to the flight controller via the BetaFlight configurator. We will go fly. Again, some short line of sight flight with black box logging enabled. After the flight, we check the temperature of the motors and check the black box log again and compare the results between the two flights if it gets better or not. Let's move to the BetaFlight configurator now. I've got my quad connected on the COM3. Connect to the quadcopter flight controller. Go to PID tuning, filter setting. So we move the low pass frequency to 80 Hz. This will introduce a little bit more delay, but it will get compensated by disabling all the static notches and setting the PT1 filter instead of by quad. So static notches are not needed. For now I'm keeping the D-term notch and setting the low pass filter to PT1. To set the stage 2 filter we need to go to CLI, gyro low pass to type PT1 should be good. Gyro low pass to HZ is our cutoff frequency for this filter, and we set it like I said 400 Hz. And also the gyro overflow detection we can disable for all axes, BATIO. Okay, I think we are good. Save the settings, recheck if it's got saved. Let's go to the fly. We take a second fly, take some black box log and compare data. So I did a second test flight, not so long as the first one and not so aggressive as the first one because currently there is a night and outside of my house is very bad visibility. So I just did 30-40 seconds hour and some little bit flying around, but this should not affect the noise spectrum. So let's open the new log file. Again, select the inner area of the flight so you can see the noise pattern is pretty the same. And we are interested in filtered data. Let's zoom in. There is a little peak at 500 Hz on the roll. axis, very similar on pitch. And yeah, so we have a few options here if we want to get rid of this noise, which is pretty small already, I guess. Compared to the value of the true signal, we can add a static notch at this frequency. Let's see what this noise does on PIDs. So I will add more graphs. I'm interested in P-roll and D-roll. Again, no smoothing, no expo. This is graph for roll, and for the cross-check purpose I add also for the pitch. P pitch, D pitch, no smoothing, no expo. What I'm looking for in the spectrum of P's and D's is how much this noise peak affecting the P or D. So for the P, yeah, there is a peak, quite visible. D, also on the pitch, 520. And on D, like 474. And this is with dynamic filters off. After the hover, the motors were totally cool, like totally cold, not heated a bit. So if we enable dynamic notch, then what happens is that most probably the most significant noise peak will be found on the right edge of the dynamic notch working spectra, around 500 Hz. And this could be the reason why to enable the dynamic notches again if we do not want to add the static notch. The downside of this is that the dynamic notch, which is centered on the border of the working center, will add quite big cutoff frequency. So the center will be on the border, and the cutoff will be pretty wide, what can cause more latency if compared to static notch with precisely selected cutoff. So for this case we can theoretically at static notch at 500 with cutoff at 400, so 100 Hz left and right width. The dynamic filter has a benefit in the cases that you hit the branch and damage the probe, so the noise frequency spectrum can shift and get out from your static notch and cause the excessive noise in D gains, which can damage your motor. So I will probably enable the dynamic filtering. If I would go for the performance, I would add one static notch with center at 500 and cutoff at 400. And if I would go for safety, I would enable the dynamic filters. So I will go for the safety. Back to the configurator and set the dynamic filtering on again. And let's go fly again. I did a third flight. Let's take a look to the log file. And as we can see, I also a little bit crashed here because of the visibility. So we don't want to cover this in the analysis. So select the range. Look to the pre-notches, should look the same. And the filter data. As you can see, the dynamic filter completely removed the peak at 500 Hz. I probably don't filter the crash properly. Let's see. Yeah, the crash is here. So now it's properly cropped, and you can see the signal is clean as a whistle. Very nice. Very nice. In this case, we could probably get rid also of the stage 2 filter, or set it really high to cause less latency. If we look to the PIDs, D, roll. Yeah, there is a lot of higher frequency noise, which is not present on P, and it starts to creep out about 600 Hz. So we can use another great feature in BetaFlight 3.4, and it is the D-term low pass filter. So I guess we can turn off the gyro stage 2 and enable the D-term low pass to get rid of this higher frequency noise. So what cutoff to choose? I would guess 700 Hertz, 650, maybe 650. Yeah, so we will set the D-term filter, low pass, frequency to 650, and we turn off the stage 2 filter. For this purpose we need to go to the CLI. We turn off the gyro low pass 2, and we apply the D-term low pass 2 to 650. Save. Yeah, low pass is disabled. D-term is enabled, and probably we can get rid of also the notch filters on D-term. Let me check the analysis again. So we have D-term notch center at 260. And D-term low pass at 100. Yeah, you can see the declining noise after the first D-term low pass filter at 100 Hz. So I guess we can disable it. We can disable the D-term. So let's do another test flight. I hope the last one. And we will be ready for the next session about PIDs. The fourth flight is complete. Let's take a look to the log. It was just a 15-second. No, that's the bad one. This one. 40-second test. Okay, so the stage 2 was definitely working for these high frequencies. Look at these. Okay. Not bad. So definitely put the stage 2 back. To get rid of this higher frequency noise. How does the motors look like? So this is the motors. Zoom a little bit. Yeah, and we are getting these higher frequencies. also into the motor, but in comparison with the normal signal it's kinda weak. But I will definitely put the stage 2 back to get rid of these noises. This is interesting. This is unfiltered data for the roll. There is a lot of noise at these frequencies. Okay, so putting the stage 2 back, and I think we are done in filters.